Hello everyone, and welcome to the tree level order print solution lecture. The problem statement was this. Given a binary tree of integers, print it in level order. The output will contain space between the numbers in the same level and the new line between different levels. So for example, if the tree looks something like this, 1 with a couple of branches, 2, 3, and then another level, 4, 5, 6, you should be able to take in that tree and then print something out like this, 1, 2, 3, and 4, 5, 6. In the Jupyter Notebook, there's a written explanation you can go ahead and check out, but we're actually just going to jump straight to the code, take advantage of some deck-like structures that are already built into Python from the collections module, and then we'll go ahead and just explain our solution out. Let's go ahead and jump to a notebook. Alright, here I am at the notebook. I already have the node class set up. This is just from the answer solution notebook, but we have left, right, and then val, classic node, class. Okay, let's go ahead and start with our function to print this in level order. We'll just call this level order print, and it will accept a tree. And right off the bat, we'll say if not tree, just return, because we know we no longer need to iterate over that. Okay, something I'm going to do is take advantage of the dex data structure, which you can actually just import from collections. So I'm going to say import collections here. And the collections module has the stacks, queues, and decks built into Python. So I'm going to say nodes is equal to collections.deck. And in this case, we pass it just that tree as the single item in a list to set up our nodes as a deck. Okay, I'm also going to set up two variables, one called current count, set it equal to 1, and another one called next count, set it equal to 0. And I'm going to say, while the length of that deck we just did, nodes, is not equal to 0, we're going to do the following. We're going to say that current node is a new variable and set that equal to nodes.popLeft. And let me go ahead and say nodes here. And what this pop left allows us to do is, since we have a deck, remember a deck we can remove from both ends. So this allows me to use this pop left method on that deck. You can go ahead and check it out just by pressing tab later on. So let me just go ahead and put a new cell here so we can just explore this a little more in case there's any confusion. And I will set d equal to collections.deck. I'm going to pass it in a list of 1, 2, 3. And then if I say d dot and then I press tab, these are all the methods or attributes I have available for me. So I can say pop left, and I can also say append left versus just a normal append, which just goes to the right. And then pop will just also go to the right. So pop and append, the normal ones always go from the right end of that deck, but I can also append left and pop left, which I can't do with a normal list. Alright, you can go ahead and review the deck lecture in case there's any confusion on that, but it's basically a list where I can pop and append things from both ends, unlike a queue. Alright, so I'm going to pop left and set that equal to my current node, and then since I'm doing that, I'm going to set current count. I'm going to subtract 1 from it. And then what I'm just going to do is print the current node dot value. And then I'm going to say if the current node dot left, and I'm going to say nodes append current node dot left. And then I add 1 to the next count. And we'll go ahead and go through the overall code in just a second. But I'm going to say if current node dot right, and remember how we use this dot left and dot right check just to see if it's basically, this is essentially if not none check. because if there's nothing there, it's just going to equal none. In this case, I'll say nodes append current node right. Very similar to what we were just doing. Current node dot right, and I will say next count in this case plus equals 1, and I will also say if current count is equal to 0, then we just finished printing that current level. So I'm going to go ahead and say print a new line, and then I'm going to reset the current count. And I'm going to do some tuple unpacking here in order to do this as next count and current count. And this is just to make sure I don't have to set up a temporary variable for this sort of switch here. So that's a nice little feature of Python tuple unpacking. And let me make sure, looks like I have an error here in line 13. Let me go ahead and remove that. Sorry, I didn't catch that. That should have been a 0. So while the length of nodes is not equal to 0, my apologies, I'm going to say this. Let's go ahead and zoom out so we can get a whole picture of the code. I'm going to take in the tree, check if there's none there, otherwise I'm just going to return. Set up a variable called nodes. It's a dec of that given tree. And then I'm going to set my current count equal to 1 and my next count equal to 0. So while length of nodes is not equal to 0, meaning he'll still have stuff in that nodes dec, I set my current node equal to the left popped out, and the current count is going to be subtracted from 1, or have 1 subtracted from it. Then I'm just going to print the current node value so I can check it. Then I'm going to say if current node dot left nodes dot append the current node left next count plus equals 1. Similar check for the current node right. And then finally, if my current count is equal to 0, I can just print a new line and reset my current and next count. Let's actually make sure this all is working before we finalize this solution. So what I'm going to do is just go ahead and set up a tree. Cell root equals node 1. And then we'll go ahead and say root.left and root.right are 2 more nodes, 2, 3. So when we print this out, we should see 1 space 2, 3. And you can try this out with a larger tree if you want. But now I'm just going to call level order print on the root. And you notice here, we didn't exactly get the spacing right. So why is that? That's because of the print statement up here. In Python 2, what I would have to do is put in a comma in order to keep printing on the same line there. So that's essentially just a print formatting issue. In Python 3, you may have to adjust this. What you could do as well is just get a new list and call it something like line2print equals empty list, and then just go ahead and print out that list and have this line be essentially an append, and then print it later on, right before you print that new line. It's up to you. That's essentially not what the question's getting at. That's just a print formatting issue. So don't worry too much about that, as long as your logic of how you're checking for the current nodes, both left and right, and then essentially adding to this count and being able to print new lines is correct. That's really the key to this. The time complexity of the solution is linear, order n, because that's the number of nodes in the tree, so it's optimal. We'll have to be able to check each node because we need to print it at least once. Alright, so again, basically what's just going on is to print the new line in the correct place, we're just counting the number of nodes at each level. And we're going to have 2 counts, namely the current level count and the next level count. That current level count indicates how many nodes should be printed at this level before printing a new line. And then we just take away from that count every time we pop an element. Once the current level count reaches 0, we just print a new line. The next level count contains the number of nodes in the next level, which will become the current level count after printing the new line, which is what this line right here is doing. Okay, then after that we just count the number of nodes in the next level by counting the number of children of the nodes in the current level. Alright, you can go ahead and check out the full explanation in the Jupyter Notebook. There's a couple of mentions to something called breadth first search and also depth first search. and we'll discuss those later on in the graph section of this course. Okay, with that being said, this is a pretty common interview problem, so make sure you know it well. And there's various ways of actually solving it. So go ahead and feel free, like you have some flexibility on your actual solution. Okay, with that being said, thanks, and I'll see you at the next lecture.